Hello and welcome to this third session. In the last couple of sessions we've been looking at the hydrogen atom, specifically the energy of the electron, the kinetic energy, potential energy, the total energy. We've gone on to consider as well hydrogenic atoms more generally, that's to say more protons in the nucleus but still only one electron, and the speed of the electron. And now we're really coming to the end of the hydrogenic case. I thought I'd throw a really nice question here to you from a past Olympiad paper. So it's a chemistry Olympiad paper, might have been 2004, it's quite an old question, you may not have seen it before. So it's about supernova, it's a lovely bit of context to this. And so I think probably regarded as quite a hard question normally, but having looked at these energies now, shouldn't be too difficult for you. And so you can see here on the screen that we've got the equation here for an electron in shell N, and it involves the Rydberg constant here, the ionization energy of hydrogen, Z, the atomic number squared, divided by N, the shell number squared. So this will be something for you to think about. So we've got some energy calculations here. In part A, we've got a transition between two energy levels. So that's the difference in two energies here for part B. The ionization energy in part C. So this is the difference between n equals 1 if it's an atom with a single electron, and actually n equals infinity, which is effectively what you get at the ionization limit. So here later in the question we're having to apply E equals HF to work out some frequencies, and then it gets really interesting at the end here where we're looking at some of these heavier elements. And so again another frequency question with the oxygen 7 plus Lyman alpha line, so again a hydrogenic atom. And then finally here we need to solve for Z in a question where we're given the frequency which we can convert to energy, and then once we found Z we found the element, because obviously that's the atomic number. So you might like to have a think and work through these questions. Pause the video, come back to it, and we can go through the answers. Here we have the answer to the first part. So substituting in the numbers into the energy equation here, Z equals 1 for hydrogen, N equals 2 for the 2p subshell, multiplied by the Rydberg. Of course, we met the Rydberg before as a molar quantity, 1312 kilojoules per mole, the ionization energy of the hydrogen atom. In the question it's given to you as just for a single atom, and so actually the value in the question will be the molar quantity divided by Avogadro's number, and so this comes out to give you that Rydberg there divided by 4, and so there you can get the exact quantity. Then on the second part here, it's the difference between two energies, between the 2p orbital n equals 2, the 1s orbital n equals 1, and so once we multiply that out, that comes to 3/4 of the Rydberg, which therefore comes to this quantity here. Now we're looking at the helium 1 plus, so Z equals 2 there for helium, n equals 1, so it comes out as 4 Rydbergs this time. So this next question now, we've having to find the frequency. So here we are, we're dividing by the Planck constant. And so again, it's this 3/4 Rydberg here for the Lyman alpha transition. And for the next part, same sort of thing, except this time because it's oxygen, Z is equal to 8, and again the Lyman alpha, and there we go, and then there we go, the last part's just dropped out here as well. So same sort of thing, except this time we're solving for Z squared, haven't been given the frequency. So yep, so Z squared comes out to about 100, square root of that 10, element 10 neon. So a bit fiddly with the calculator working all these things out. If we'd been asked to do it in atomic units, it would have been so much easier. So of course in atomic units, the Rydberg is half a Hartree. So we'd have just had to make that substitution in there, and then we wouldn't have been faffing around with all these awkward numbers. Right, so here we go. Now onto a 2-electron atom, helium. So we think of helium as being such a simple atom, you know, only got 2 electrons, you're only filling the very first orbital. But actually helium is a way more difficult problem than hydrogen, because of course you have the electron-electron interaction to think about, which you didn't have in hydrogen. And so what we do, approaching this from first principles, what we would normally do is think about approaching it with some approximations, and ideally the simplest possible approximation. If it works, that is marvelous. If it doesn't work, we just need to make the approximations more and more sophisticated. In fact, it turns out that we can't actually, it's actually impossible to get analytical solutions to this problem, so we're always going to be working with some level of approximation. And so, you know, we go for the low-hanging fruit first, see if there's a really easy approximation. If not, then we kind of pursue something a bit more complicated. And so what really simple approximations might there be? For example, and here are kind of 2 extreme cases. So when you're considering one of the 1s electrons, just basically pretending the other one isn't there. So that's to say there'd be no shielding of the first electron by the second electron. And on the other extreme, we could assume that the second electron is perfectly shields the first electron. So, you know, it spends all its time between the first electron and the nucleus. So this is our other extreme. And we're going to be considering the total energy of helium. So obviously it's a nonsense that both electrons could perfectly shield the other. But yeah, we'll just go with it for the moment, as it's an assumption we're trying out. And so we've got these exercises here. What would be the total energy from each of these assumptions? And so if we do this in atomic units, it should be quite simple. So you might have to think about that for a little bit, bearing in mind these assumptions. And then once we've done that, we can test it with data. And the great thing about atomic structure is there's so much data. Ionization energy data, spectroscopic data is there in absolute abundance. So the great thing is we've got the real, genuine energies at our disposal here. And so here are some experimentally determined energies which we can use. So we've got the first ionization energy of helium, the second ionization energy of helium, and the conversion factor to go from molar ionization energy into Hartree. So you're asked to use these real values to determine if either assumption is useful or not. So I'll give you a moment to think about that. You can pause the video and I'll go on to the answers in just a sec. Right, so looking at the answers now. So first of all, if we neglect how one electron shields the other from the nucleus, if we forget the effect of one of the electrons, then actually we're back to a kind of hydrogenic situation where we're imagining it's only a 1-electron atom. But of course you've got 2 protons in the nucleus, Z equals 2, and so putting that into our hydrogenic energy equation, the energy comes out as -2 Hartrees. That's minus a half Z squared over N squared. So see Z is 2, squares to 4. But of course there are 2 electrons in helium, so if we want the total energy of the helium atom, we need to multiply that answer by 2, and so we get -4 Hartrees as the total energy. And remembering the conversion between Hartrees and the Rydberg, that means it'll be 8 times the ionization energy of hydrogen. So that is if the second electron is doing no shielding at all. And then going on to the opposite extreme, which is perfect shielding, if the second electron is always between the first electron and the nucleus, it's effectively going to cancel out one of the positive charges in the nucleus. So as far as the outer of those electrons is concerned, the sort of net electrostatic pull able to get into the nucleus would be with just one of the protons left in the nucleus. And so actually this is a hydrogenic atom, effectively. So we got 1 electron, if the second electron kind of cancels out one of the protons in the nucleus, that will just leave you with a hydrogen atom. And so treating it as a hydrogen atom, just like hydrogen, the energy would come out as -half a Hartree, the total energy of the electron. But of course, since this is helium, we've got 2 electrons, we have to double that to get to the total energy, and so that makes the total energy -1 Hartree. So here we've got these 2 kind of extremes, where there's no shielding whatever, on one hand and there's perfect shielding on the other hand, and we get -1 and -4 as the answers in atomic units. And so in an ideal world, when we look at the actual total energy of helium, if the actual total energy of helium was very close to -1 or -4, then great. It means this really simple approach, one or the other, has worked. So let's see what the real energy is. And so for the real energy, we have to sum together the two ionization energies. So the first ionization energy takes one of the electrons out to sort of infinity, effectively, or basically free from the nucleus. And of course, this is what we define as 0 of energy. And then we need to add to that the second ionization energy to take the second electron out to infinity, free from the nucleus. So when both electrons are taken out to infinity, this of course is how we define the 0 of energy. So the amount of energy you need to put in to take both electrons up to 0, you put a minus sign in front of that, and that will be the total energy of the electrons. So we add the two ionization energies, you get this number 7,623 kilojoules per mole, divide it by our conversion factor 2625.5, and what do we get? We get -2.9 Hartrees. Bit of a disaster really, because that's not very close to 4, and neither is it very close to 1, or -4 and -1. So, oh well, it means there wasn't a really simple way to work out that energy. Never mind. So, we've got to try a bit harder now to think about what we can do about this, and this will take us in the direction of our next line of attack. And now this is looking at the shielding a bit more specifically. So as I say, we've considered the sort of no shielding versus perfect shielding. And so what we're going to do now is we're going to take the realization that the shielding is intermediate. We clearly have some shielding but not perfect shielding. And so what we're going to try and do is quantify exactly how much shielding we do have. And so here we introduce the idea of the so-called effective nuclear charge, and this should be something you've come across before in chemistry. Effective nuclear charge is often spoken about when looking at trends in the periodic table. You might have looked at trends in, let's say, atomic radius or ionization energy across period 3. Quite likely that effective nuclear charge came up in that discussion. So for example, in helium, the 1s, if you take one of the 1s electrons, it doesn't quite experience the full Z = 2, 2 protons from the nucleus. It will actually be reduced slightly by the second electron spending some of its time between the first electron and the nucleus. And so we're going to quantify that with this S shielding parameter. And so the shielding parameter is going to be the reduction in the proton charge due to the shielding of the second electron. And so this definition here, that ZF, the effective nuclear charge, is the proton number minus this shielding parameter. So what we can do actually, in the helium case, we do know what the total energy of the helium electrons is. It's -2.9 Hartrees. And so what we can do is, given that we know the energy, and given that we know the shell number, for example, we can actually work out, sort of backwards, what Z would have to be to solve the equation for the energy of the electrons. And so this is the next little exercise for you to think about. And one little tip I'd give you is that remember that the total energy is the energy for the 2 electrons combined. But this idea of the effective nuclear charge, we're going to be substituting this into our equation for 1 electron, its energy. So the first thing you probably want to do is think about what must be the energy of 1 electron in helium. So once you've got a value for that, we can then put that into our energy equation. E = -1/2 Z² over N squared, except in this case we'll be solving for Z to see what the atomic number, as it were, looks like from that 1 electron perspective. In other words, we'll be actually solving for Z effective, and then from Z effective we can work out what the shielding parameters must be. And this was actually a very important problem that was solved quite early on in the study of this early atomic physics, that was done by Slater actually, I think back in the 1920s, I think it was, and he was working out these shielding parameters using experimental data. And so I'll just leave you with that to think about, and at the start of the next session we'll go through how it's done. So until next time.